All right, so picking up where we left off on the last video on number 14 here. Notice this one does have a little calculator icon up there, which means you can use a calculator. For this function, we're given a rational function, and we're supposed to determine what is true about these points, -2 and 3. Ask us some questions about continuity, discontinuities, things like that. Now, generally, if we want to figure out if a function is discontinuous at a certain point, we would want to factor the bottom, find the zeros, determine if those are also zeros of the numerator as well. However, if you go to factor this, you're probably going to get stuck because it's not going to be something that you can factor so easily. You would think maybe grouping, but grouping doesn't actually work out on this one. So factoring is not the best way to do this. However, we are given that we can use a calculator. And another strategy that you can do rather than just try to solve something is take the answer options and then basically see which one of the answer options is true by plugging in things like that. So that's how we're going to approach this. First thing that I would do is just go ahead and graph it in your calculator, since we can use a calculator. Plug it into your y equals. And your graph looks something like this. So this point here is at, looks like -2 approximately. So it definitely looks like, based on the graph, what's happening here is that there is a vertical asymptote right there, right? Because the function, as we're approaching -2 in both directions, is going down to -infinity. So it definitely looks like there's a vertical asymptote at -2, which means we can eliminate the first two. We can verify that as a fact. Some other ways I'll show you, but we can probably go ahead and eliminate those two. So then we just have to consider if f is continuous at 3 or if it has a removable discontinuity at 3. Now, on your graphing calculators, you're not going to be able to see like there's a little hole there. So if out here at 3, if there's a little hole there or not, your graphing calculator isn't really, advanced enough to show you if there's a little hole there, because there's not enough pixels on it. So there could be a hole there at 3, or there could not be, but we cannot see that on our graphing calculator. It's going to look solid whether there's a hole or not. So what we need to do is figure out if there is a hole. How we're going to do that is simply just plug 3 into our function, and specifically the denominator. So if I were to do f of 3, and really I just want to look at the denominator, like I said right now, I would get 3 to the third, which is 27, plus 3 squared is 9, minus 3 times 8 is 24, minus 12. So I actually end up with 36 minus 36, which is a 0 on the denominator, which means it's undefined. So since it's undefined, that means there actually has to be some sort of discontinuity there. So it's got to be actually choice D. That's really the only option, because it is discontinuous at 3. Now, as far as confirming that there's a vertical asymptote at -2, if you remember, vertical asymptote is a 0 of the denominator that is not 0 of the numerator. Whereas this 3, if we were to actually plug it in the top would actually give us 0 as well, because we get 27 minus 27. So 3 is actually a 0 of both. The -2 should actually only be a 0 of the denominator if it is a vertical asymptote. So if I were to just go ahead and plug it in, f of -2, on the top I would get -8 plus 18. So it will not be 0 on top, you'll see. The bottom, I'll get -8 plus 4 plus 60. Plus 16 minus 12. And we will get -20 and +20. So we do get a 10 on top and a 0 on the bottom, which means that would be a vertical asymptote. All right, the next problem, number 15. For this one, this is a piecewise function, and we need to make this function continuous. Now, how we make something continuous, for a function to be continuous, this is the definition of continuity. The first one is that, well, the limit as x goes to whatever c exists. And for that to be the case, we said that the limit as x goes to c, from the left equals the limit as x goes to c from the right. The second condition is that f of c exists, as defined. And the third condition is that the limit as x goes to c equals f of c. So those are kind of our three conditions if it's going to be continuous. So at the point 3, we can just kind of start and work our way down, is that the limit from the left must equal the limit from the right in order for the limit overall to exist. So using these two conditions, you can see it splits there at 3. This would be the limit from the left. I guess x goes to 3 from the left. We would use the top one. If we're coming in from the right, because that's greater than 3, we'd use the bottom one. So what we need to happen is the limit from the left equals the limit from the right. So in other words, the top equation must equal the bottom equation at the point 3, because the limit from the left has to equal the limit from the right. So then all we're going to do is plug in 3 for the x there. So this becomes 3 squared, which is 9, plus 2 equals 3 times 6 is 18, plus k. And then just simply solve it. We get 11 equals 18 plus k. So k would equal -7. And that's actually all there is to it. From there, we could verify that f of c exists because you would just plug in 3, it would go into the top, that's 11. And then we could also verify that from either side it equals 11 as well. So that one's going to be A. Okay, next one. So which of the following functions are continuous on this interval 0 to 2? So probably the best way to figure this out is figure out if there's going to be any discontinuities or if any values, like for instance, 1 is on the interval 0 to 2. So see if 1 makes any of these discontinuous. I think it'll be pretty obvious. So we look at the first one, f of x. 1 sort of right in the middle of 0 to 2, so that's an easy one to check. If you plug in 1, f of 1, well, that's going to become 1 squared minus 1 on the bottom, 1 minus 1 on top. So it'd be 0 over 0. So that is definitely discontinuous at 1. So that one we can rule out. Notice that this is not a calculator question, so you can't just plug these into your calculator either. Cross that one out. Okay, the next one, g of x. So let's go ahead and look at this. If you were to plug in 1 into that one, g of 1, it'd be 1 plus 1 over 1 squared plus 1. So it'd be 2 over 2. So that is continuous there at 1. And really what you would need to figure out, is there any place that it's going to be discontinuous, this function? And the answer is no, because if you set the denominator equal to 0 and try to figure out what would make that discontinuous, you would get x squared as -1, so it would be the square root of -1 plus or minus I would be your answer. So there's no real numbers that would make this thing discontinuous. So that's going to be continuous. And the last one let's check is the h of x. This one's maybe just a little bit more challenging if you don't know as much about the natural log function. But again, I'm just going to plug in one number that will probably make it fail. It just happens to be in the middle of the interval, which is 1. So we get the natural log of 1 squared minus 1. All right, now we get the natural log of 0. So you might be thinking, well, what is the natural log of 0? And the answer is, this is undefined. How you might remember that is you need to know what the natural log function looks like. It looks like this. It never crosses the y-axis. It gets infinitely close to 0, but never actually can equal 0. So it's good for values greater than 0, but not values 0 or less. So that's undefined natural log of 0. And again, you wouldn't necessarily have your calculator for this question, so you couldn't have the luxury of plugging it in your calculator and seeing. If you do plug in natural log of 0, you'll see it says error domain, but you just need to know that you can't necessarily rely on that. So that would be discontinuous. So the only one that is continuous is number 2. I can't regulate the calculator use so much in this online format, but can know that for the AP test that will be the case. All right, number 17. So the continuous function f is positive and has a domain that is greater than 0. If the asymptotes of the graph are at x equals 0 and y equals 2, which of the following statements must be true? All right, so if you think back to that AP handout worksheet that we did, this would be a good strategy to use for this. And I might even just draw a little axis just to help you sort of visualize what's happening here. If we have an asymptote at x equals 0, so the x value of 0 would actually mean right here, right? So this is saying it has a vertical asymptote at x equals 0. And then it also says at y equals 2. So at y equals 2, we have a horizontal asymptote. All right, so let's think about what that means. For this vertical asymptote first, what this is saying is we have some function that as we approach 0, it might maybe look something like this. There's a vertical asymptote, right? So as we approach 0, as x goes to 0 from the left, and as x goes to 0 from the right, we're approaching either infinity or negative infinity. So let's look for some sort of statement that says one of those two. So either one of these should be infinity or negative infinity, right? As we approach 0 from the left or the right. So it looks like this one is a possibility here, C, and A are both possibilities because it says the limit as x goes to 0 from the right is infinity, so those would be possibilities. This one would definitely not work, and that one doesn't even mention limit as x goes to 0, so that wouldn't work. So we're down to A or C. From there, let's try to figure out the horizontal asymptote portion of that. And remember, for horizontal asymptotes, that's always going to be a limit as x goes to positive or negative infinity. So what we're looking for is a limit as x goes to either plus or minus infinity, and that has to equal 2. It has to equal a constant to give us a horizontal asymptote. So of these two that are left over, it looks like this one is the good one. Limit as x goes to infinity, positive infinity in this case equals 2. Again, it could have been negative infinity. Either one would have been fine, but this one satisfies both. This one does not. It has them switched there. So the answer is C. Number 18. The function g is continuous at all x except x equals 4. The limit as x goes to 4 equals infinity. So which of the following must be true? Well, if you think about what we just said on the last one, if you've got, and you can even just draw this out if that's helpful. You've got the limit as x goes to 4 equaling infinity, which means from both sides it has to be going up to infinity, right? If the overall limit is infinity. So there's definitely a vertical asymptote there. So x equals 4 is a vertical asymptote. That would be C. For number 19, let the function here, if the line y equals b is a horizontal asymptote of f, then b equals. Okay, so think about, in this case, think about infinite limits. Whenever you see horizontal asymptotes, think about a limit as x goes to either plus or minus infinity. So to figure out a horizontal asymptote, we have these infinite limit rules, which if you remember, when you have a rational function, you're just going to look at the powers of, the biggest powers on the top and the bottom. And we sort of had three scenarios. We had if the powers were the same, then we take the ratio of the leading coefficients. If the denominator power is bigger, then it's going to go to 0. And if the top power is bigger, then it's going to plus or minus infinity. So remember that little table that we have. And so in this case, we do need to multiply these out. If we FOIL the top, we get 2x squared minus 8x minus 3x plus 12. On the bottom, we got to FOIL that as well, x squared minus 2x plus 1. So we do have equal degrees, meaning equal highest powers, both are squared. So in this case, we take the ratio, if we're finding the limit as x goes to infinity, take the ratio of the leading coefficients. So in this case, it would just be 2 over 1, so it'd be 2. That's all there is to it. But you do need to remember those rules so that you can just, oh, that's what I do. It's too easy. Okay, next one, number 20. All right, we got a big function going on here. Which of the following is a horizontal asymptote? So again, horizontal asymptote, immediately what you should think is a limit as x goes to plus or minus infinity. So if we take the limit of this, all we need to do is find the biggest powers. So biggest power here, negative 7x to the fourth. And we got an x to the fourth on the bottom as well. They're the same, so we will take the ratio of the leading coefficients. So negative 7 over 1, which is negative 7. So we've got a horizontal asymptote at y equals negative 7. Number 21. Let f be a function that's continuous on that closed interval. Which of the following must be true? So whenever you have a scenario like this, the first thing that I would do is draw this out. What's happening here? So we've got a closed interval 1 to 3. So I'm just going to draw 1, 2, 3. And it says f of 1 is 10. That means at 1, the y value should be 10. It doesn't have to be exact. So this is 10 here, right? And then at 3, f of 3, x equals 3, it's up to 18. So we get up there to 18. Sorry. All right, and it's continuous. So we don't know what this function's doing, but we know it's continuous, and it starts here, and it ends here. So whatever happens to this function, we know that in some way it's got to make it up to there, right? It might be just as simple as that. We know that there's no breaks in it because it's continuous. It might do, I mean, it could do any number of things. Maybe it could go way down to here and then back up. We don't know. But we know that it's continuous, and it makes it from point A here to point B. So which of these must be true? All right, so the first one is that f of 2 is between 10 and 18. So let's consider this. At the point 2 here, this one, does it have to be between 10 and 18? Well, it could be, but it doesn't necessarily have to be. You can see in this case it was in that first function I drew. However, the second function, this scenario that I drew, it actually looped way down here, right? So 2 is actually like, I don't know, negative 10 at that point. So it doesn't necessarily have to be. It says must be true. It doesn't say could be true. It says must be true. So this doesn't have to be true because it could dip down, or it could even just stay flat level at 10 and then just jump up at the end. We don't know, but it doesn't have to be then. Second one, f is increasing on the interval. Well, it has to be increasing on part of the interval, but it does not have to be increasing on the whole interval. As you can see, it's decreasing here, and then I made it increasing here. So it does not have to be increasing on that whole interval. Next one, f of x equals 17 has at least one solution. So what this is saying is that the y value has to be 17 at least one point. This one is true because if we're going to go from 10 up to 18, at some point we had to cross 17, whether it be this function or this in the red one or the green one, or any function that I draw. If I'm going to go from 10 to 18, then I got to cross 17 at some point. So if you remember, this is the intermediate value theorem. It actually gives you a little hint up there at the top of the screen. On the AP test, it's not going to tell you, hey, I'm referring to the intermediate value theorem on this question. But this is where we want to use the intermediate value theorem, which states that if you have, two y values and it's continuous, so in this case 10 to 18, then the function has to hit every single number in between that. So it's got to hit 10, it's got to hit 11, so it's got to hit 11, 12, 13, 14, 15, 16, 17, all the way up to 18. All the numbers in between 10 and 18 will get hit at least once. So this one does have to be true because the function does have to equal 17 at least once on this interval by the intermediate value theorem. All right. Next one, f of x equals 8. And actually, sorry, this is actually some different notation here. That actually has a little, you can see like kind of a little apostrophe up there. That's actually f prime of x, which is actually a derivative, which I haven't learned yet. So you might not have even noticed that, but that one will not be true. And this bottom one is actually an integral, which we haven't learned yet either. I didn't realize those are answer options, but that's not true either. So we found the one that works, and it's something we know how to do. So it is C. Sorry if that was confusing. Okay, number 22. Of the following tables, which best reflects the values of the function for which the limit as x goes to 7 equals 6. So for this, we're just going to be looking at our table and figuring out limit based on the table. The x values have to be approaching 7 from both directions. The confusing thing on this is looking at the x versus the g of x part of this. But we know we want the x values need to approach 7. So we need to approach 7 from both directions, which means we would want numbers like 6.9, 6.99, 6.999, and from this 7.01, 7.001, those would be our x values. So in this case, the first one we want to x out because it's approaching 6. You can see there, it's approaching 6. So with these next three, they could all satisfy at least that part of it. And then this is referring to a y value, so the y's need to be approaching 6, which means the g of x in this case. So in this one, we are getting from both directions closer to 6 and closer to 6, so that seems like it would work. This one's getting closer to 6, but that's getting close to 7. This is 6 and 6. This is, I don't know what that's going to, and this is 6, but that's definitely not going to 6. So B is the only one that satisfies both the top and the bottom. All right, next one, best interpretation of the limit as x goes to 3 equals 5. So basically, do you understand what a limit actually is? So first two say that the value of the function is, well, you can rule those out right away because we know that a limit is not saying the actual value of the function is. We know it's saying as you approach this x value, this is what the y value equals. So you can eliminate those first two. And then you just have to determine from there, this is the limit as x approaches 3. So that's got to be C. And that the y value f of x approaches 5. So that's going to be C.